Okay, it's 9:20, so I think let's just start and then we'll have the rest catch up. So today we are going to go into a little bit of the coding for the von der Waals network. At this point, I want to check first that I've seen people have submitted the Hopfield assignment, and I'm in the midst of grading it. So, and I think everyone should be okay. Just want to check for the backprop network so far assignment. Anyone have any questions and want to clarify as you are working on it, which is due next week? Yeah. Okay, and we'll see how it goes. If you need more time, we can extend it. But if you have any questions in between, do raise it up. Okay, if not, then how about for last week's, I pull up the notes, the key thing about last week is the theory behind the von der Waals network and this fancy diagram here basically, because this is what we're going to implement today, just to refresh your memory about what we talked about last week, right? So any questions about the theory or the reasoning behind the von der Waals network and what it's meant to test? What is the aim here? What's the purpose of this model? Any questions? Okay. No? All good? Okay. I'll just have to add one thing is that nowadays, so this is kind of like the early implementation of like the idea of convolution, okay? Which is that you might have a local pixel or patch of space in a graphic, right? And you want to encode like the local visual properties of that graphic. And in convolutional neural networks, which we will talk about at the last class we will introduce, it is about summarizing. You have a spatial kernel and you kind of summarize the local visual properties and you kind of convolve them. And as you do that, you develop some higher level notion of, oh, there's like a cat somewhere in the picture, anywhere in the picture, right? So in other words, it becomes spatially invariant. Doesn't matter where the cat is, you see the cat in the picture, right? That's our experience. So this is kind of like an early, very, very primitive beginnings of the idea that there is spatial binding, as we talked about, and because of the spatial binding, you get self-organization, and it is not a property, so to speak, of the neural network itself, okay? But some sort of, at least interaction between some predetermined, as we talked about, genetic, architectural system or mechanism that interacts with the way the physical world is organized, and therefore you get this self-organization, okay? All right, so, a sec here, I'll turn this off. Okay, so if there's no question about the theory, I just highlight to everyone that there's all these papers that are interesting. You should read it if you can, if you want to find out more about orientation selectivity. As I know, things have changed. We know quite a bit more about orientation selectivity than Huber and Wiesel did in 1963. But more or less, it remains to be the case, all right? That's how our neural systems are wired, okay? I think we know a lot more about how special details and very equally cool new stuff, all right? But the fundamental organization principle still remains, all right? So, I don't know. I think it'll be interesting for you guys if you find out more new things about how the brain is self-organized beyond just this kind of thing. For example, we realize the brain has things like gradients of depth, right? How deep you process. This one is about like one flat area and then like how there are lines or there are colors or whatever, right? But then our brain also has depth. So there's that kind of organization. And then there's temporal organization. Our brain has distant time, like we remember our memories long time ago from when we were kids, in a different part of our brain than the recent memory. So there's also this time dimension of self-organization in the brain as well. So this initial idea of self-organization due to the brain's own genetic mechanisms interacting with the environment and then giving rise to this organization that we see. Okay, this is something that is of very, very deep interest and very much application, because if we understand how that works, maybe we can sort of develop better models or more brain-like models at least. Okay, and it might come along with its own benefits that if we just do it from a pure mathematical point of view, maybe it's a bit harder. You know, it's because biology has maybe solved some of the problems already, and we just need to copy it if we can understand it. Okay, all right. So today proper, what we will do is, as usual, kind of go through the Jupyter Notebook instantiation of the theory that we talked about last week. And a disclaimer as well that so far, this code that I have, it seems to be working, but I haven't thoroughly validated it yet. I do suspect that there might be some bugs, which I will be sorting out, and hopefully next week when we evaluate the model, that it will be sorted out. The key reason is because, as usual, I coded it in R, and now I brought it to Python, and it works on the outfront, on the surface, but I do suspect that some of the operations I'm not tweaking it very, very correctly. The good news is I do have the R instantiation, and obviously that works, you know, and I will be putting it up. But in any case, I think it's better to transition to Python, and that's what I've been busy working at also. And bear with me that takes a while, right? Because I mean, it's already very fast, I think, with AI help, you know, nowadays. But you still need humans to, right? I mean, that's just the fact, right? Okay, to validate what AI generates, which sometimes, it's not bad already. I have to give it credit. Yeah, it's already not bad, so I'm not going to diss it. I think it does a pretty good job. Okay, so if you can follow along with me on this link here, which will bring you to the Jupyter Notebook. Let me hang on. Just updating it. So this is a Jupyter Notebook, which is the instantiation of the R. Let me check if did I give you guys the R version? Hang on. Should have. Let me check what this is. Oh, it's not going to open it here. Doesn't matter. Anyway, so if not, I will put it up. The R version can also be run on Google Colab, because Google Colab also has a R runtime. So you can change runtime type. So this is. It looks like normal code, but it's written in R. For those of you who work with R, you will realize the syntax, okay? And you can also use Google Colab to run R, or you can change to Python, or now they have Julia, which is pretty cool, okay? Julia is supposed to be the best. Yeah, question? You can't? Oh, okay. Can you try? Do you have the link? No, you can view. This is weird. How about now? Oh, wait, no, not the R. The R should be open. Hang on. This self-organization, yeah, this one I haven't set. Hang on, give me a sec. How about now? Can you view it? Can you 吗？可以了哈。OK， All right, so this is the this self-organization IPy notebook is the Python version. The R version has a R on it, and I don't think you have that link yet. So I'm not going to confuse you, so I haven't put this one up yet. I might do it later, okay? But it's just to let you know that the original thing was coded in R, so it's like here, all this is all R language, okay? And the full code is here. It's like if you just run this cell, it will work, okay? But I've been trying to port this R thing to the Python version, which is what you guys see right now, okay? And this is what we will go through today. So I just want to highlight the disclaimer that the Python version, the R version works, but the Python version, I'm still working out the kinks. I do think it works, but maybe it needs there might be some places where I'm not translating it correctly. And hopefully we'll sort it out by next week. But it works sufficiently for today's purpose, okay? To kind of show you how to implement the theory we had last week as a code implementation. All right, so let's go to the notebook. And this mission or this assignment that you will do for the third and last assignment for this course is to try to implement the von der Waals-Berg network, okay? And the idea is that it is a model of V1 orientation columns because that was the mission that he set out to do in the first place. And it instantiates unsupervised learning in the sense of that the V1 has this orientation columns that are graded, right? And clustered and graded clusters, if you want, okay? And so this is just a bit of the overview. And so we want to define the problem as usual, okay? And the problem is essentially we want to make an artificial neural network that shows self-organization, okay? Specifically, what type of self-organization you have to define as well. Just like what I mentioned, there is temporal self-organization, there is complex abstractness self-organization. Here we are talking about clusters and gradients of these clusters along the dimension of orientation selectivity, specifically around the columns of the visual system, the visual gray matter, okay? All right, and these are some details which we already covered in theory, so I'm not going to go through them again. But basically, we are going to implement this architecture using standard learning rules, specifically autoencoding, which we all know already, and activation functions, which is the ReLU, which we sort of know, and because we already know the sigmoid shape, and we also know the binary learning. Sorry, why is it learning? It's linear. Hang on, regularized linear. This is great because I can immediately correct it. There we go. Okay. Regularized linear unit, not regularized learning unit. Okay. We already know the binary linear unit, which is either outputs either 0 or 1. Here it is 0 if less than the threshold, and the actual value if it is greater than the threshold. So that's ReLU. Okay. So it's not hard to implement. We know that, and we also want to see whether if we do it this way, whether our network will show the self-organization that we observe in biological neural networks. Okay. All right. And these are some references, and we will take a look at my assignment that I submitted when I did this course back in my long time ago. And we will need to do this because I want to show you guys a very critical picture, a figure that is there, which we will need, we will use, which is this one, okay? And I'm just going to leave this here first, and we'll come back to it later, all right? So you guys know you can have the link to that as well, and in your own coding or in your own consideration. Okay, so so any problems about that? Okay, so as with any coding neural network, we want to also, apart from knowing the aims and the goals, then we want to make things even more concrete by specifying the data table. Now, here's the biggest problem in this entire thing. Not really the code itself of the neural network. It's the irritating fact of how do we implement the a stimuli data to teach the neural network about orientations in the first place, okay? So in neural networks, you will find, apart from dealing with the neural network itself, actually quite a lot of time is also spent dealing with the data that you feed the neural network. In the past two types of models, Hopfield and even the earlier single layer perceptron, and then in the backprop, we didn't spend so much time about the stimuli. The stimuli were very simple, it's just binary words. And we spent a bit of time by talking about what they mean and how to set it up to do our testing. But it was more or less quite straightforward. But we know the real world, and that's why ChatGPT and LLM are so powerful now, is because they sort of solve the data problem, okay? It's not that you can't have the neural network, it's that how do you get the neural network to deal with real data? And real data is not binary in its base, at least in the way we interact with it, is not primarily, or directly as a binary format, right? Real data is at least analog, the way we define it, and it's very rich and varied, and it has spatial binding, okay? So actually, in order to train a neural network or to validate the neural network, we first have to get a good handle about, well, how do we convert what is real, our experience, into something that the neural network can digest and learn from and then use, right? Okay, so this is the unique part about this programming, is that we actually have to spend a bit more time than usual to deal with the format of our data. And what exactly is this problem? So this is what the point here is trying to say. Key distinction in VDM is that the unit positions, okay, means like usually we have a vector of ones and zeros, and the position of these ones and zeros doesn't mean anything. It's just that that unit is 1 or 0, has nothing to do with its neighboring unit, right? Okay. So these unit positions, for VDM, these positions are not arbitrary, unlike in previous cases. Okay? They have meaning. The relative position of a given input with respect to other input units, this has meaning. That is, their inter-unit distances have meaning. All right? The position, if you say the position has meaning, it's not arbitrary, what are we trying to say actually is that the distances between them are not arbitrary. They have meaning. Okay? And because of this, we want to have a set of stimuli that sort of encodes this idea that the unit distances have real distances, and moreover, that these inter-unit distances have no bias, meaning that we want to give every location equal chance to contribute to the training, all right, as it is true in real life. Before we are trained, our eyes are trained, every position in space is equally important. After we have trained, we realize, oh, maybe the center is more important than the side, etc., right? So, but how do we instantiate a stimuli set in which all locations are at first unbiased, equally important? The ideal case in ideal geometry mathematical world is a circle, right? In a circle, every point is equally distant from the circumference. Every point on the circumference is equally distant from the centroid. Not so with any other geometric figure, not the square, not the rectangle, not even the triangle, so to speak, if you want to say the edges versus the vertices, not the same. Whereas a circle, every point is equidistant. That's the definition of a radius. However, a circle is an analog version and it has so-called infinite resolution, right? And then that becomes hard to code for digital binary format. So the next best thing is hexagon, okay? Where let's say the points are equidistant, and they are equidistant in like up, down, left, right, and diagonal. That way we can get the orientations very easily. So we will see how that is implemented later on. Okay, so for digital format, centroid and vertices of a hexagon is a reasonable approximation of a circle. Okay, all right. And we use hexagon because you can go octagon, you can go heptagon, etc. more and more. But then that becomes unnecessarily complicated, right? So the hexagon is kind of like the minimal, nice, manageable circle-like, what we call quantized circle. Okay, it's quantum circle, right? Okay. We thus have to devise a base transform function so that we can then more effectively work with hexagons, because unfortunately we do not live in a hexagonal world. We live in a Cartesian world, right? X, Y, Z is a continuous three-dimensional notion. We do not have hexagonal patches all over our experience. We're just trying to apply that onto our real experience in order to solve this problem, okay? So this is the sort of semi-problem before we get to the bigger problem. All right, so how do we solve that? Well, first, obviously, we have to set up our notebook with the modules that we need. And as usual, we're not going to use any PyTorch, TensorFlow, or anything. We're just going to use basic array manipulation, NumPy, and plotting functions. Some nice plotting functions, and I like Plotly. You can use anything else, but Plotly seems to work for the most part. Okay, so the first semi-problem, we want to define a function for transforming between coordinates, okay, of a hexagonal grid manifold. So what this means is, this is fancy word for saying that, imagine we live in a world where every step we take is a hexagonal coordinate. Okay, it means if I jump here, this is one hexagon. If I jump to another place, it's another hexagon, another hexagon. So every step I take is defined by hexagonal units. So this will be a hexagonal grid manifold. Okay? But this hexagonal grid manifolds, because we live in a Cartesian manifold, is that every step we take is a new instance of x, y, z, right, in continuous 3D space. So we want to have a way to transform between this real continuous space, that's what I mean by Cartesian manifold, and a hexagonal space, okay? You can imagine that what we are trying to do is kind of shape the hexagon such that every hexagon step we take is equivalent to a Cartesian step, or every Cartesian step we take is equivalent to a hexagonal step, okay? Those of you who are very into math, you will know this is something to do with Riemannian geometry, which is basically you have two bases, two manifolds, and you're just trying to find a mapping between them, okay? It's a tremendous field of mathematics and stuff like that. But that's essentially what you're trying to do, is at least for this problem, very limited problem, okay, not a very generalized one, of just trying to say, if I want to move x, y, z steps in what direction, what is that equivalent to in a hexagonal coordinate system? And vice versa. If I move this way in a hexagonal system, what does that mean when I move in the Cartesian x, y, z step? I need to do this because we live in the Cartesian world. We visualize the hexagon from a Cartesian perspective. So in order for us to make sense, we have to have it operate in hexagonal world, and then after that, put it into our Cartesian world so we can appreciate that, oh yeah, it makes sense, okay? Otherwise, to us, it's very hard to visualize, okay? So this is what this step is for. And to do that, I have this nice link. You can click onto it. And you can take your time to read it, but I'll tell you that this is a nice geometry lesson, okay? But I will tell you that what we are going to use is we're going to use, because this website introduces you several strategies to convert between hexagon and Cartesian coordinates. We're going to use this first one, which is this one. The flat top orientation, which is this one, okay? This one, versus the pointy top. We don't want the pointy top, we want the flat top, okay? Why? Because, and that's why I said, we have to go back. This is what von der Malsburg did, okay? It's flat top, not pointy top. If you rotate it, it's pointy top, okay? He used flat top. So that's one thing we want to note, because we're trying to mimic the paper first, okay? So we want to use this one. And if we use this one, it's very simple. As long as we know the radius, which you call size here, okay, which is the distance between the centroid to the side vertex, then the height of this flat top is just exactly square root 3 of the size, okay? And the width is twice of the size as you, this one is easy. Why is it like this, okay? Well, if you are interested, I did put up the notes. For those of you who like a little bit of more math, I did put in the notes here, hexagonal plotting. You take a look, I just drew it out, okay? Some trigonometry for you, if you want. Okay, you can go and figure out why the flat top, and then that's 1 square root 3. I didn't do it directly, but I can tell you that you have to do something like that, right? You have to know the theta angle, and then you know the hypotenuse and the length and all that. If you calculate it, you will know, yes, the height is square root 3, basically, okay? I'm confident that you guys can do it on your own time, okay? But I will not spend too much time. So we will use this strategy to do the, because you see, what this allows us to do is to move from a Cartesian basis. You see the square grids underlying it? That's the Cartesian manifold. To move between a Cartesian manifold and then translate that to the so-called hexagonal spacing that would be equivalent, okay? I mean, there will be, in between there will be nothing, but it's just about what resolution you use. But that's why you can jump between one basis and the other. Because one basis, this is the Cartesian size, is equivalent in the hexagonal manifold as well as the Cartesian manifold, right? This size, when we say, let's say this size is 2 cm, then it is also 2 cm in the hexagon state and in the Cartesian state. And because of that, we can then calculate. Because size is 2 cm, then, but if I move in the hexagon world, then I will, if I'm moving in the vertical direction, then I'm moving by some factor of square root 3 times size units, right? But in Cartesian world, I'm moving by however different scales of units, right? So this is what we are using. And so we will use this code to jump between hexagon and Cartesian worlds. Disclaimer here also, I do have my own code. I wrote my own code in R to do the translation between hexagon and Cartesian, but I figured that now that the AI is so smart, I literally just told the AI, okay, can you please create for me a function where I can translate between hexagons and real Cartesian coordinates? And this is what it gave me, and it works perfectly. And it is sort of what I wrote. So I was like, okay, I'll just use it then, because it's already in Python, whereas what I wrote was in R. And so you can see that it is exactly implementing this, that some, if I tell it, so I have to tell you the input. It needs, this function needs you to tell, okay, I'm now trying to create a grid, okay? And this grid is defined in terms of this grid that this function will give out will be the x and y coordinates in Cartesian space, but based on what the hexagonal space locations are. In other words, if I have this hexagon here, what x, y in real space is it? And then if I move to the next hexagon, right, then what x, y space is it, right? So what it's doing is tell me how many rows and how many columns of hexagons do you want, and the spacing between them. Then I will tell you, this function will tell you the x, y, z, the x and y coordinates of each point of these hexagons. Okay? It's a bit abstract now, but when we implement it, you will see how it works. Okay? So you need to tell it how many rows and columns of hexagons you want. And just to let you know, one row of hexagon is actually like this, two rows of these dots. Okay? This is one row. And how many columns is every column like this? So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 columns. All right? Whereas this is only one row, like that. Okay? So let's deal with something easier first. I want to create this stimulus. Okay? This stimulus is actually 1, 2, 3, 4, 5, 6, 7, 8, 9 columns wide. And it is 3, 1, 2, and 2.5, but you need to be in integers, so you can say 3 first. So this is 9 columns, 9 hexagon columns by 3 hexagon rows. Okay, actually it's half rows, but that's the scale that we are talking about for the code. Okay, so in other words, this code you need to tell it 3 rows, 9 columns with the spacing. Let's make it easy to be unit 1. All right? And if you give it this information, so it will then iterate for every row, for every column that you want. I am now going to compute the Cartesian XY coordinate of the points that would be defining these hexagons. Okay? And it's doing it by saying, okay, for column number 1, given that your spacing is 1, and we know that the relationship of the height is going to be square root 3, so this is what we are going to use. And then for spacing 1.5, that's what we're going to use. So this is exactly the formula from before. And then it's going to do some offset because we want to have it like a nice visualization. Otherwise, it's going to be squashed. Okay? So this is just for making it so that it's a bit more equal. Okay? And then it will spit out the coordinates and return an array of x and y's. Okay, we'll see how this works. So let's run this. Any questions about this at this moment in terms of this very abstract code? Okay, it's no problem. Then I'll show you how to use it. Let me see. Oh yeah. This is just to return the x and y coordinates, okay? But I want to visualize these x and y coordinates. So I need to have a plotting function. So this is my plotting function. If you see my plotting function is a little bit complex now, but let me take you first to the key part, okay? So the outer wrapper of this code is a subplotting wrapper. And what that does is, so I can plot 9 things on one figure like this, okay? But let's focus on, let's just even plot just one hexagon first like this, one area like this first, okay? Now, and that would be this part here. I have a series of x and y input, okay? And these are the inputs from just now the transformation function, okay? So I will give it these x and y coordinates, and I will also give it an on list. This on list tells me which of these coordinates are on and which of these hexagonal points are off, okay? So that if the x and y coordinate is on, then I will plot a black circle of size 10. If that x and y coordinate is off, okay, MP where on list is 0, so it's off, okay, these x and y, then that marker, I still want to plot it, but I will make it smaller, size 3. Okay? This way, I do it this way because you'll see later. Then I can have these hexagonal points, and where it is on, it is big, and where it is off, it is small. And that way for me, I can visualize things a little better. Okay? Now, I'm going to not go through all the detail of the code, but other than that, the rest is a subplot wrapping, meaning I plot one plot, then I plot another one, then I plot another one, and in fact, I want to repeat it 9 times later. But I can also say just do it one time also. I have the control to do that. That's the way I set up the code. Okay, so I have, did I run this? So I'll load this function first. Best way is to see how it works, okay? Then you will see, you will see how, you will be able to appreciate how it works better. Okay, so I want to, I'm now going to plot something here, and it's first going to seem very, very messy, okay? Because you won't know what it means yet. But I just used that create hex grid to get the XY coordinates, okay, in line 14 here. And then I use these XY coordinates. I have an on list. Right now, my on list is basically all ones, means everything is on, okay? Every coordinate is on. And I want to do this because I want to show you that, that if you then put this XY and the on list into this VDM hex plot function, which is the plotting function to plot these XY coordinates to visualize it, this is what you get, okay? Now, I'll break this down, so we'll take some time here, okay? So you can see behind is the Cartesian gray grids. Can you see it? Okay? And on top of that, you see these dots. They are the hexagonal points that, that quantize the underlying Cartesian space. Okay? And every coordinate of the hexagon points are on. Okay? So I can change things. I can make the size now different. This was 8 rows. I remember it was 3. Oops. And it was 9, 1, 2, yeah, 9 and 3 rows. If I do this grid, I want 3 rows and 9 columns. You'll see what I get. Okay, a bit clearer. Okay, right. I have this. You can see there are 9 rows. 1, 2, 3. 9 columns. 1, 2, 3, 4, 5, 6, 7, 8, 9. And there are 3 rows. If you say this is 1 row, this is 2 rows, this is 3 rows. Okay? All right? Okay, why do I want to do it this way? So if we go back to the paper, look at this stimuli. Let's see if I can zoom in here. Doesn't zoom into the figure. Huh. Okay. I think I can download it. Hang on. Yep. Okay. All right. So you can see here, this hexagon is starting with the bottom 3 units, 4, 5, 4, 3. Okay. So I need to start my code where I can actually set a system or a basis where I have enough coverage to have 3 units, 4 units, 5 units, 4 units, and then 3 units. So if you see there's a hexagon here, this shape. Can you see this shape? Okay. So I want to get rid of this top row, and I want to get rid of the corner points. Okay. And I can do that, and I'll show you how to do that later. Okay. But we have to start out like this first. So here we have the beginnings of where every point in this hexagonal space is not biased. There's no special bias in terms of the distance. Okay? So we have this starting basis now, and we can use it to then qualify later on what we're going to do. So here, so this first part kind of starts this coding or extracting of coordinates between hexagon and Cartesian spaces to jump between the two, and then as well to visualize it. Okay, so we have these tools in place now. The next tool, the next implementation or application we want then is that, well, so I want a hexagon that looks like this. Okay, that looks like this. It doesn't just look like this. These are hexagonal coordinates, yes, but they don't give me the von der Mausburg stimuli that I want. Okay, so how do I do that? Well, this is a 3 by 9. And we note that in the 3 by 9, we have embedded in there the hexagon we want, but then there's some extra stuff around it, right? So how do we get rid of it? Well, so again, we have a 3 by 9 and the spacing is 1. Now we realize that actually where the hexagon is in these locations. This unit here, this one, okay, these 3 units, these 4 units, these 5, 4, 3 units, right? Which unit is this in terms of the hexagon array, right? There are a total of, I believe, let's see, 3 by 9 would be, 3 by 9 should be 1, 2, 3, 4, 5, 6, 7, 8, yeah, 27, right? Should be 27 units. So if you have a 3 by 9, but you only want a subset of units, how many units are there? I can tell you that there are 19 units in this hexagon. Okay? So which 19 units out of these 27 units in total? Okay? So this is going to be unit 0. In Python, you start with 0, 0. Okay? This one is going to be unit 1 because we're going by columns. Okay? This one is going to be unit 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, which is total 27, okay? This is 0. All right, so we need to pick out unit 2, 3, 4, okay? 2, 0, 1, 2, 3, 4, 5, 6, yeah? We need to pick out 2, 4, 6, and then 6, 7, 8, 9, 11, 13, and 15. We need to pick out these, select out these units to plot, but don't plot these other units. So that's what this is doing, okay? I have told this code that I don't want to plot all the x and y coordinates. I only want to plot the second one, the fourth one, the sixth one, the first, third, fifth, in this order, okay? 7, 9, 11, etc. So I have to pick out these, okay? There might be a smarter way to do this, okay? But for me, what I did is, by the time I figured out the smarter way to do this, it'll be like one whole week. So I just manually just do it, and I did it in like 10 seconds, okay? All right, for now it works. If you want to scale up this, you don't want to do it that way, right? But we are not talking about scale here, we're just talking about understanding. So I just picked out, okay, 2, 4, 6, 1, 3, 5. So these you will see give you 19 units, right? So if you count, there are 19 elements in this SEL select vector, okay? And I have my on list, which is that the first row of on list says that this is a 19 unit word, okay? This says that for the first pattern, for the first stimuli, so if we go back to this pattern, this first stimuli, okay? This is on, this is on, this is on, this is on, the rest are off, correct? So in other words, position, if I go back to this, position 4 is on, 2 and 6 are off. Okay? Then position 1 is off, and 3 and 5 are on, and so on and so forth. Okay? So using this way, I can then say like, I first select units 2, 4, 6, 1, 3, 5, etc. That will give me this shape, this general shape. Then in this general shape, I want to turn some of them on, some of them off. And by doing this differently, you can see the second row is different, the third row is different, the fourth row is different. By doing this differently, I should instantiate these 9 different patterns. Can you see the logic? Okay, so step by step, okay? We first have a way to get XY coordinates that map onto hexagonal position, rows and columns. Then we can visualize these coordinates, okay, up on top of a Cartesian basis, which is the fundamental basis we work with anyway. Okay, so but we can visualize it like this. This visualization is not selective. It visualizes every point, but we only need some of the points that define the hexagonal area that we want to work with. Okay, and so we select those points that define our total hexagonal area of 19 units. Of these 19 units, some of them are on or off depending on which pattern we want. We have a total of 9 different patterns for 9 different orientations. So we have 9 different on-list vectors. This will be the equivalent of the data table that we've been working with for Hopfield and backprop, right? We have the Walsh patterns with the autoregressor, or we have the whatever other orthogonal or non-orthogonal patterns associated with the output, desired outputs. This would be the input patterns that we want to test. And we have 9 of them, okay? And because, as sort of hinted earlier, we are going to use autoregressor, so we do not have an output, desired output. The desired output is the input. It's an autoregression problem, okay? And we want to see by doing this whether there's self-organization, evidence of self-organization. Okay, are you with me so far? With this, I haven't run it yet, so it's hard to see, but this is the principle. Okay, the rest are just kind of tools to like wrap around, like subplotting and putting in titles and labels and adjusting the size. Okay, the rest of the codes are just about doing that. But the fundamental, the heart of it is about this, getting these coordinates plotted, selecting them, and selectively turning on or off the subset that we want. Okay? Now, so if I run this, this is what you get at the bottom. Okay? All right? Look cool? So you can see that first you get a vertical stimuli, okay? Then you get it slightly rotated clockwise a little bit, clockwise a little bit more, okay? So 12 o'clock, 1 o'clock, 2 o'clock, 3 o'clock, no, wait. Yeah, sort of, right? This is 3 o'clock. Then, you know, rotate some more until you get like 5 minutes to 12, something like that, okay? All right, so then you get 9 different orientations for your data table that you want to teach this neural network to do. So we see we haven't even gotten to the neural network yet, but we've spent a lot of time fiddling around with the format here. And it's important, okay? It's important to do this because it gives us an appreciation that, yeah, reality is not so simple, right? And we have to help translate a little bit so that we can make our tests a bit more valid, okay? Now, I do also want to qualify. Do we really, really need to work with hexagons? And the answer is no, we don't. We can always work in real Cartesian space. We can feed it real photographs, you know, which are X by Y thing, and then it's grids. We can do that. In another assignment, in another course where we are worrying more about like, can we make it to replicate the picture and all that, yeah, go ahead and do that. The goal here, however, is specifically to replicate von der Malsburg. And why? Because von der Malsburg was interested in the question of orientation selectivity and orientation on self-organization. So this is not about can it regenerate the stimuli, can it capture deep properties. This is about when I get the network to do something like that, does it have self-organization? So it's very different thing, okay? So we have to appreciate that. And you can do the same with flat grid if you want. In fact, in your assignment, if you decide to do that, it's fine. You don't want to fiddle around with this, it's fine, okay? But I'm just sticking true more to the paper, at least for the purpose of this class. All right? Okay? And plus, I think it's cool. If you have this tool, it's cool because maybe you can find some application for it in other scenarios as well. Okay, so any questions about this? We have the data table now. Now we have this visualized stimuli. And I will jump to this first before we take a break. Apart from visualizing the stimuli, so this is like one patch on the retina, right, of 19 units to encode the orientation in this part of space. But this retinal input is going to feed to my V1 cortical layer, isn't it? My V1 cortical layer is going to need to be bigger in order for me to see whether there's orientation columns as I traverse along a gradient, isn't it? So in other words, my V1 cortical layer also needs a hexagonal visualization, and it in fact has to be bigger than just these 19 units. In fact, it has to be 169 units, okay? And how do we do that? Well, I use the same sequence. I define an 8 by 29 hexagonal area, okay, which is this. So if I go back to this tool here, here was a 3 by 9. I'm going to do 8 by 29, and that's what this looks like. It's a much bigger area than just now because we want to be able to see this. Right? We want to see if, so if I zoom out a little bit, feeding the network these 9 patterns will get the visual cortical layer to have some sort of organization, which is like, they say these nice clusters like that. Initially from no clustering or minimal clustering to very, very defined clusters, okay? So we need to visualize a big hexagon here from amidst of this unselective array. We want to select that big 169 units. How do we do that? Well, it's here, okay? So I have 8 by 29, spacing is 1. These are the 169 units that define that big, that hexagon amidst that big total array. Okay, and if you ask me how I did this, again, I could do it in a smart way. I did it in the R. R version is the smart way, okay, which is like, I actually know how the height and the width are related, so I can calculate. But this week, I didn't have time to think so hard to translate to Python. So I just labeled, like, I literally counted all the points that are here, and I counted that this one is unit number 7. This is unit 7, this is unit 9, 11, 15, 17, 21, etc. And then I did it for 169 units. Okay, so this is what it is. Very manual, very dumb. Okay, yeah. There is a smart way to do it, which is about the height and the width and all that, but I didn't have time to figure it out. In any case, it does the same purpose, all right? It will extract the selective units that you want that define the base array, and just for visualization, I can turn it all on, and I can label it like this is going to be the excitatory layer, which is part of the cortical layer. And let's plot it out and see. So originally, it's an undefined hexagonal basis. Then if I did the selection and I turn all the selected units on, I should get my excitatory layer looking like this, which is now all excited, okay, at the moment. So now I have my hexagon translation for my stimuli and for my neural network in place, okay? And later on, we are going to then do the coding to train it and then to test it. Okay, any questions so far? We're going to take a break after this. Any questions about this setup so far? Just to let you know that this is we are here. Okay, we have defined the problem, we have the overview, we've defined the problem. Now we were worried about the data table. Okay, so we have defined a function for transforming between coordinates, define a function to visualize the states, on states of those select coordinates, visualize the manifolds before selection, visualize the stimuli, which is the selection from the manifolds, plus turning these selected ones on or off to instantiate our stimuli, and then we visualize one cortical layer. Okay, the steps of what we have to do to get to where we want to get to, okay? All right, if no questions about that, then we will take a 10-minute break. Actually, let's take a 13-minute break and come back at nice 10:30, and then we will move into the training code. Okay? All right. Okay, let's continue. We good? All right, just to reiterate, this is what I had to do, okay? So if you guys want to figure things out on your own, you want to consider something like that. This is the stupid method of doing it, not so smart method, at least. Okay, is that what I had to do was to say like manually. I mean, it took me 30 minutes as opposed to it might take me a whole week to do a smarter way, and which is you have to fill in everything though, okay? And so your eyes have to be very good too. And after a while, you kind of get dizzy. All right, am I doing it right? No, nope, I did it wrong already. See? It has to be here, here, and here. Okay, right. So and by this token, it should be actually another row because I'm doing, yeah. Okay, you have to fill in this part also. Why? Because this is position 0. This is I'll use a different color. Let's use green. Is it or green? Okay. This is position 0. This is position 1, 2, 3, 4, 5, 6, and you see 7, right? 8, 9. 10, 11, 12, so on and so forth. Okay, so if you do it this way, you can select the units you want out of the whole array of 29 by, I believe this is 29 by 8 or 8 by 29. Sorry, 29 by 8. Okay, right? If it's row 1, row 2, so row 1, row 2, row 3, row 4, 5, 6, 7, 8, and there's 29 columns because this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Okay, so if you have this, you can totally define the entire hexagon array and also picked out the units that you want that define this shape within that total array, and then kind of you don't want these, you don't want these, you know, you don't want this row, you don't want this, you don't want this, and you don't want this. So by only selecting that array, you get your hexagon. Okay, so this just to visualize, graphically make it very concrete what was involved. Okay, so let me clear this, and then we'll go back to the code. All right, so here we are. We have this E layer, we have the stimuli, the 9 patterns. So how do we train this E layer to activate to the 9 patterns in a cortical gradient organized kind of way? This is define the function to train the VDM network, okay? And I'm calling this VDM unsupervised learning, U-learning, okay? It takes, as always, if you have some pre-trained weights, you can feed it to it, or you can define it in an unpre-trained way, in an initialized way. And I specify that if there is no trained array, then you set W, the initial weights, to be an input vector of length, set W to be a list of length of, a list, I didn't delete, to be an input vector, that's all you need, okay? A length of the input vector, okay? The length of input vector, the row and the column of the cortical layer you want. In other words, the initial setting for W should be the length of our input vector is 19, right? Our stimuli have 19 units, correct? Go here. This stimuli, the input vector, has 19 units. So W, the first entry, the first unit, the first element will be 19. And the rows and columns of the cortical layer, well, we just drew it out. It's going to be 8 by 29, right? Okay, so that's the size of our array. And so it will take the values from this W here, okay? This is 8 and 29. I've set it here already. I've hard set it, but I can take it in as a variable as well. Okay, and some of the other parameters we will talk about later, but basically the first thing you want to enter is this specification, and also you want to enter the input, which is the stimuli, the 9 patterns that we will, array of 9 patterns that we will want to train it, and the theta, which is the activation function threshold. Okay, so these 3 are the important things. The rest are some hyperparameter and some hard coding things. Also note that we have this thing here right at the beginning, which is to say the number of stabilization iterations. This will come into more clearly later. What happens is when we train the network, okay, we let it have 20 iterations to change its weights for one pattern. Then we go to the next pattern and we train it and then have 20 iterations, and then next pattern, train it for 20 iterations. Okay, that's how this goes. And then we do this for the 9 patterns, 20 times 9. And then we do this 20 times 9 phase, we do it 100 runs. So it's 20 times 9 times 100. That's the number of total iterations that we will do. Okay? Why do we have to do this is because you will see the way that the network activates, it's got the dynamic part to it, right? It first excites the cortical layer, excitatory layer, then excites the inhibitory layer, and then the inhibitory layer inhibits the excitatory layer, right? And this kind of dynamic, you let it happen, you let it loop 20 times to reach some whatever stable point, okay, within 20 iterations. And you do this each time for each pattern. Okay, so that's just the outer loop and hard parameter setting. Why is it 20? Well, because von der Marsburg says so. Okay, you can go and change the number if you want, all right? But again, we're just, for now, because it's already so complicated, let's just stick to the von der Marsburg first before we play with anything else, okay? So this is what it is. And so let's assume the case where we have, no pre-trained model. So we want W to have 3 pieces of information in W. First is the number of input vector units, which is 19, and the row and the column of the cortical layer we want, which will be 8 rows and 29 columns. Okay, so that's what this is here. The spacing is the same, and this is what I already did just now. Like, this is selecting the 169 units and using it to plot using it to instantiate the coordinates that define my cortical layer. Okay, then I will initialize the weights that we have. So here I should bring up the blackboard again. So case in point, if you look at the blackboard, just to remind you, we have a few variables to encode, okay? Or a few variables to instantiate. First, of course, is the input vector, which is ASK, which is a 19 by 1 vector. Then we have the WSE, which is the weights that connects the excitatory layer from receiving inputs from the input layer. And because the cortical excitatory layer is 169 units, therefore, weights array is going to be 19 by 169. Then we have the within excitatory layer connections, which will be 169 by 169, okay? And this is the excitatory units, 1 by 169, okay? And then the excitatory to inhibitory weights, 169, 169, and backwards, the inhibitory to excitatory weights, 169, 169. So we have 1, 2, 3, 4, 5, inhibitory neurons, 6, and 7. 7 things to initialize before we can implement these equations here to determine the pre-activation state of the excitatory units. Okay? So all this. So we will have, well, the number of excitatory units, the number of inhibitory units, the input to excitatory weights, the excitatory weights, excitatory, inhibitory, excitatory. Okay? So we initialize these variables first. All right? And then we apply some genetically predetermined weight hyperparameters, which is that we first have to calculate, okay? What are these genetically predetermined parameters? Would be, remember, what is hard-coded is that when a neuron is so-called born or created, right, in the cortical layer, it is located, right? It is split, or mitosis is split from the mother neuron, okay? Or it's it developed in a way that it has its neighbors at certain locations, right? It has its neighbors, and it has its neighbors' neighbors, and then it has its like distant relatives. They're not related. So you have to code how far each pair of neuron is from each other. So in this iteration here, I first determine, I select unit 1 in the excitatory layer, okay? That's NE, okay? The number of, for all units in the excitatory layer, first select one unit. Then select a second unit. What is the distance between these two units? That's dy and dx. Okay? So I select one unit, I select another unit, what's the distance? I select this unit, I select another unit, what's this distance? I select this unit and another unit. Every other 169 to 169 pairs of distances, I will be calculating that, the distance, inter-unit distances. Okay? And note, this is important. That is why we have to have the hexagonal coordinates in Cartesian space and vice versa. Because the distances are defined in Cartesian space, right? Although they are hexagonal quantized steps, but their actual distances are in real Cartesian space. So you want hexagonal unit vertex 1, hexagonal unit vertex 2. Okay, what is the Cartesian distance between these two? Or the Euclidean distance between these two, rather. Okay? All right? So that you can, you need to know this unit's hexagonal position, but then also what is their real Euclidean and Cartesian instance. Okay? So this is to calculate the distance between these two. All right? And the y coordinate of the second unit minus the y coordinate of the first unit, x coordinate of the second unit, x coordinate of first unit. This gives you the triangulation, and then you can use that in the classic formula, right? Square root of the sum of squares will give you the distance between these two units, right? Triangle, right? A squared plus b squared equals c squared. So if you want c squared, you just square root the sum of a squared and b squared. Okay, this is simple trigonometry. Pythagoras. Okay, so you get this, and then you will know this. Basically, what this is the rounded distance. Okay, between these two units. If the distance is equals to unit distance, this is what this does. Okay, if this is equals to the unit distance, which means that these two neurons are neighbors, correct? The unit distance is the nearest distance, right? From one vertex to the other, from the centroid to the next hexagonal unit. So this means if you are neighbors, then your weight, WEE, between these unit 1 and unit 2 is going to be equals to P, whatever P is. So this is the genetically determined weight between an excitatory unit and its immediate neighbors. Okay? Remember, von der Mossberg is not interested in training these weights. He's saying that I already know that there are some genetic predisposition. A unit is going to be more connected to its neighbors because of genetics, because of whatever the way the brain grows, right? Okay? I'm asking on top of that, are there going to be beyond these determined things that determine the self-organization? So I fix this first, okay? All right, so lines 52, 53, okay? Okay, now, this is for E to E, okay, for a given pair. And obviously you loop through all the possible pairs, but let's just take one pair first, okay? Then another thing is, what about if you are talking about E to I, okay? The excitatory to inhibitory layer, okay? Again, I want to say what's the distance between these two units. Now, we imagine that the inhibitory units and the excitatory units are kind of co-located. So whatever distances there are, it is only in the across the plane that we are interested in distance. We are not interested in between layers kind of thing, at least for this instantiation. Okay, so across the plane, these two units, if their distances are less than or equals to the this is not unit distance, right? E separation is going to be, I believe, E sep order 1. Let me check. Oh, it is also unit. For now, it's also unit. Yeah. I lost myself. Yeah. This is also effectively unit distance for now, okay? Because this is 1 and it is spacing. If it is less than or equals to, then it is set to R. Yeah, well, it is about the excitatory first. So the excitatory still excites its inhibitory neighbors, okay? Then the key thing is here. This is not 1. This is 2, okay? IE sep is 2. You'll see later when I set, because IE sep is about the order. This order variable, okay? Which is one of the inputs to this function here. And I'll highlight where it comes in. Just hold it in memory. So when you do coding, you have to have a good working memory, okay? You need this order to tell you what are the factors by which to set this separation between EE, EI, and IE neurons that you want to use this factor to control what's the range of your influence, okay? So that's what this order means, the order of which this neuron exerts or receives influence, okay? So the order is different depending if you are EE, EI, or IE, okay? So that's where this comes in. And so, so here we apply the order to scale the spacing that we want. In the IE separation case, if you see later, the order is 2. What that means is for neurons that are the neighbor of my neighbors, my connection with them is Q. And it's hard fixed this way. Okay? So in these 3 different lines, I am applying genetically determined weight hyperparameters to the EE, EI, and IE connections. Okay? All right. And they incorporate the distances between them and the factors that I want of the order. Okay. Good? Okay. So now we're going to go on, okay? Then, now, if there's pre-trained weights, then we just copy the pre-trained weights and the parameters, all right? So this is, and I'll always have that contingency. Now we're going to start the actual training. And again, we have to initialize the excitatory neuron states, the inhibitory neuron states, and then which is overruns and over iterations, because just like if you remember with the backprop, we have to do batch updating. We want to hold things, we don't want to just apply them, we want to hold them because we want it to be fair for all patterns, right? So that's, although we know that the brain is not fair that way, okay? But at least for the coding part, this is why we have ASET and ASEDT is about runs and iterations within each run, okay? So that's why it's T and DT, smaller and smaller. All right, and we also have placeholders for the actual signal that is sent out. So the activity state is sort of the pre-activation state. And the signal is the nonlinear modulation of the pre-activation state. So signal E is the activation function applied on ASE, okay, which is the ReLU, okay? So sig E is ReLU of ASE, basically, okay? As it is, sig I is ReLU of ASI, okay? All right, and then we initialize weights as empty matrices at a given time. Let me see. I have it as time because then I can track how the network evolves over time. So this is different from the first setting. Okay, this is the first instantiation. I hard set it first, and then I note that this hard set won't change, but at the first time I can code it. I realize I actually don't need this. Yeah, you know, again, I copied it from the R, and I haven't made it efficient yet. And some other encoding and some other variables these are just for evaluation and monitoring. All right. Now, so the meat of it, we're going to start with run number 1. In run number 1, our excitatory neuron states and inhibitory neuron states are nothing yet, and our weights, okay, are I believe our weights WIE has been. Did we set it yet? Yeah, we have. Here you go. This is important. Our weights are initially set to be random uniform numbers, okay, from 0 to S. What is S? In von der Mausberg, S is 0.25, okay? And what does S means? Means the maximum activation state of the excitatory neurons, okay? So in other words, at the initial state, sorry, not maximum excitatory state of neurons, maximum connection weights of the input to excitatory connections. So in other words, the weights at first between the input to the excitatory layer, they are random and they are ranging from 0 to 0.25. This is the initial. This is what von der Mausberg did. Okay, so this line 40 instantiates that. Now, because it's randomly determined, we don't want it to go out of hand because random could be whatever. We first normalize it. And so we actually, before we even do anything, we already normalize the weights, given whatever the random initialization did. So the random weights have some variation and some range. And so we apply the fancy, if you remember the formula in the paper, is the S over 2 sum of all the variance, then applying it to the full array, and then modulating the original array values, and that would give you the normalized. This will be the normalized input to excitatory weights. Okay, so we apply normalization first, and just to remind you, we have to normalize because if you don't, it could go to this. In theory, it could go to infinity, and that doesn't make sense. Okay, our brain has some normalization operations, so this is the implementation of that. So we normalize it, and then on top of this normalization, we then feed it now some new information, and so we loop through the first pattern, the vertical line. So we select the input, okay, as pattern number 1, or the first pattern is pattern 0, okay? And we set such that the excitatory states of the units are at first 0 first, and the input as well, 0 first. And then now we go to the stabilization iteration, which is 20. So do this next thing 20 times. What do we do 20 times? Well, we first have a running log of the excitatory and inhibitory neural states. And so for each neuron, excitatory neuron, this is the ReLU. Okay? Sig E is equals to the ReLU of ASE minus thresholded by theta. Okay? So we calculate the actual signal coming out from the excitatory neurons given the initial normalized weights and the input pattern first one. Okay? And then we compute the inhibitory weights. All right? This is the inhibitory weights, and this is going to be excitatory to inhibitory transpose, okay, dot product with the sig E, all right, where sig E is the signal coming in from the excitatory. And then the sig I themselves will now be the ReLU of this pre-activation ASI. Okay? So we have the excitatory to inhibitory stimulation now. And then we can compute the excitatory activation states, which is the MP dot product between the input weights to the excitatory layer and the input pattern. Okay, so we have the input pattern kind of pre-activation state, okay, put here, and then the excitatory state, which is the dot product between the excitatory neurons and each other, okay, and then the inhibitory state, which is the dot product of the inhibitory back to the excitatory layer. So you see the cycle that we're doing. We have the input to the excitatory. Well, at first we have the excitatory to the inhibitory. Then we have the input to the excitatory. And then we have the excitatory to excitatory, and then the inhibitory back to the excitatory. So we have all these components now in the very, very first iteration for the very, very first pattern. Then we say the excitatory layers, units, new pre-activation state, which if you go back, we are trying to instantiate this part here, this yellow pre-activation state, right? The sum of all these WAs, okay, is this one. The dot product of IE by input, small I, okay, which is input excitatory by input, plus the dot product of the EE by the excitatory layer units themselves, their state, their signals, minus, because it's inhibitory, the inhibitory to excitatory weights with dot product from their inhibitory neurons. So this line 130 instantiates this pre-activation state function here. Okay, any questions? This is the logic and the flow of the code, okay? And then we just, get an assessment of how much deviation. So it's the deviation of the new activation state with the old activation state of the excitatory layers, and then we log it, okay? And then we append this for this iteration, and for these 20 iterations. And then we finish the, this might be, maybe this is it. Okay, so then we have, theoretically, this should be doing it for this pattern, okay? And then learning it, the learning is, this is the learning, I should do this here. Updating rule is right here. the learning rule is a autoencoder, right? The input pattern and the output of the excitatory layer, to the extent that they are dot product, which is the parts where they agree, okay, weighted by some learning rate, which is h, is a constant, okay. This level of agreement where they agree, weighted by the learning rule, by the learning rate, is then used to update the previous input to excitatory weights, i.e. small i.e. For this pattern, okay, due to this pattern. And so we keep doing this, and then eventually we do batch updating again. We then make the new IE to get the IE from all the patterns, the IE weight from all the patterns. So this is batch updating. Okay. All right, then we log this so that this is kind of like a checkpoint, a snapshot of this one round of change. And then we do it over and over and over again for 100 runs, 20 iterations each run for each pattern. Okay, and then that's it. Then when you are finished doing all of that, you will have your weights for the input excitatory over time, your weights for excitatory to excitatory over time, which shouldn't change, right? Because we don't actually update them, we just fix them. But it's useful to have just for evaluation. Your weights for E to I to E, and the activation unit, excitatory states, and the inhibitory states, and the change of these states for each iteration, and the other metrics. Okay? So any questions here? I will now load this code. Okay, so now I have my VDM network, VDM learning network, which I will feed it some initial settings that I want because I don't have any pre-trained weights, and the input that I want, the theta, the threshold, the order in terms of the space of influence, the radius of influence. Okay, so I have this function now, and I will now try it out by my simulation. Before I do that, first, any questions about the training code? Yeah.
The very end into the batch updating part.
Yes.
I already understand why you always do input to excitatory instead of excitatory to excitatory.
Right. Yes, this goes back to what we said. Von der Mausberg is interested in looking at whether a neural network can have self-organization given that it has some fixed, known, biologically determined way of connecting already. So where we talk about in real life, what we mean by that is some things are fixed by DNA, right? Your neurons are going to only connect synapses with its neighboring neurons or its neighbor's neighbors. It is not going to synapse with neighbor, or like things that are really, really far away, okay? And it's going to be fixed in this way in a sense that these neighbor connections, we know that they change, but let's just say, let's fix them first. So they are not allowed to change, they are fixed, and because that's making it harder, right? If they are fixed, all the more you don't expect any organization to happen. Correct? Because they're fixed, nothing to reorganize, they're fixed. Okay? So he's sort of saying that let's assume first that all these things, these contributions are fixed first. Then, so this includes the E to E, the E to I, and the I to E connections. Let's fix these. Okay? Let's only allow the input to excitatory to have the degree of freedom to change. Meaning, let's only allow the environmental input to change what this network, okay, given that this network has some fixed parts. Does that make sense? And then in this scenario, do we see self-organization happening? in the way the network activates and responds. Okay, does that make sense? Yeah. So that's why. That's why only IE is updated. Small IE is updated, and the rest are fixed. It also makes it much easier to code, right? But theoretically, you're free to try. Let EE, big IBE, and all that be free to update as well. See what happens. I don't know. I haven't tried that. Yeah. Any other questions? Okay, if not, then the moment of truth, we let it run, and then, we'll see. And what do we do when we let run? Well, we set up the simulation, right? So our input is 9 different patterns, and as you see before already, this instantiates the 9 different orientations. And our hyperparameters are that our W is 19 units with 8 rows, 29 columns, okay? 19 input units feeding into a cortical layer that has 8 rows and 29 columns of hexagon bases, okay? And we hard set so that the EE weights is set at 0.4, the EI weights are 0.3, the IE weights are 0.286. Don't ask me about these numbers, this is just what von der Mausburg said in his paper, okay? The maximum strength of the input excitatory weight is 0.25, as we said before. The growth rate, the learning rate is 0.05, okay? And the threshold is, theta activation is 1, threshold is 1. And the order, which is the range of influence for any given unit, is such that if it is an EE unit, the order is the neighbor, which is 1. For the EI unit, the order is also 1. For the IE, however, it's 1 beyond the immediate neighbor. That's the range of influence, okay? And the number of total runs we want to do, let's say we do 500 runs, 100 runs, 1,000 runs. This is again, like how long do you want to let the visual system look at this stimuli before you take, like you let it stay like, oh yeah, I see a line or something like that. Or I see different lines, okay? Okay, so this is the setup. The data table and the hyperparameters that we want to run, and we set it and we feed it into the VDMU learning function that we had, and it's going to take a while to run these many iterations. It's not too bad, just a few seconds. Okay, it's done. So its output, when it's done, its output would be the IE weights, the EE weights, the EI weights, the IE weights over time, over runs. What is really of interest to us is this fella here, ASE over time, okay? ASE are the excitatory layer unit activation states, pre-activation states, okay? Because we want to see if I now give it stimuli, like a vertical line, does the activation state like activate according to some clustering pattern and all that, right? Okay, so I will probe and plot the ASET, the last one, on the 9 different patterns. So if you, here, just to illustrate, NP shape of ASET is going to be 500 by 9 by 169. Okay, what does this mean? It has 500 runs, right? So the first run is the untrained activation state, okay, of the excitatory units. And the 500th run, the last run, is the trained one, right? Trained after 500, updating of the IE weights, okay? The small IE weights. Okay, what is 9? 9 are the 9 different patterns. okay, the 9 orientations. And what's 169? Well, it has 169 units in the excitatory layer. So what we are interested in is the last iteration. So in line 5 of this probe for plotting, okay, we are interested in the last iteration for a given state, and let's say state number 8, which is, let's say, the almost back to normal line, back to vertical line, okay? And because ASE, so if you are interested in what it actually looks like, let's do ASE T, last iteration, let's say for state 8, okay? We can even do state 0 if you want, but let's just do state 8. What does it look like? 169 values. It looks, this is the range of activity. Ranges from 0 to almost 2 or something like that. Okay? So it is not binary. That's the first thing. The activation state of the excitatory layer is not binary. It has a range. But we just want to know whether it is on or off, right? Remember, ASE is not the sig E. Sig E is the ReLU of ASE. ASE is the pre-activation state. So this is the pre-activation state. So we need to apply the ReLU function onto these values to make it sort of more binary, sort of, so to speak. We need to threshold it, in other words. Okay? So how do we do that? This is why I said it here now. I binarize the excitatory layer for plotting. So for any given state, okay, if ASE is greater than theta, which is the threshold, set it to 1. If it is less than theta, set it to 0. Okay? So that my on list now, my on list is going to be a binary vector of 169 zeros and ones to say which position is on, which position is off, given the ASE pre-activation information. Got it? Okay, so using that, I plot my selective XY coordinates so that I want only 169 units. Okay, and this is my, after 500 rounds of training, this is my activation state of my excitatory layer for pattern number 8. Let's try pattern 0. It's going to be different, okay? And you can try pattern 1. I can do this more efficiently. I can use the form and I can, select it and all that, but I haven't done that yet. Okay, this is pattern 2. Immediately, I can tell you that there's something wrong with my code. Okay, because at 500 iterations, it's not really showing you nice clusters, isn't it? Yeah. Okay, let's see what it looks like when the iteration is not the last one, but the first one. Okay. But for the same state. It seems like almost there is clustering, but not really neat. Okay, let's take a look. Yeah, kind of get an idea what's happening. But so this is before it's trained. Okay, and then after it's trained, you saw it just now, and you can imagine it in between. See, that's why you need all these evaluators and all that. It's not just about coding; it's about how do you evaluate. So actually, you need to put in place some markers that you know will be important for you later. Okay, and you kind of get a picture. I know kind of maybe what's wrong here. I think my normalization is off. Okay, it's not really normalizing correctly, and that's very likely because the normalization I translated it from the R. Right, using AI, and maybe it's not A, not so I. Okay, right, and I didn't have time to go and think much about it yet. Okay, so hopefully it will sort it out. Okay, So why did it go from nice and quiet to something looking a bit more noisy? It's probably the normalization, as I said. Okay, the normalization is making things messed up and more noisy than it is actually refining it to be kind of settling it down, I suspect. Okay? So this is how you would sort of, a basic way of using this now. And, you know, as usual, once we get this settled, then we worry about what are other things we can do to evaluate, how do we tweak this so that we can evaluate our model or expand it or apply it in other situations. But this is the core, okay? We want to be able to set up the basis for the hexagonal translation. Then we can feed it the hexagonal orientation inputs. Then we implement the VDM architecture with the genetic determined weights plus the updating of the input to excitatory weights, doing batch updating for all the patterns. Then we run it. Then we evaluate, compare the activations of the excitatory layer before training and after training by visualizing the excitatory layer's activities for every given input pattern that we have. So this is the general approach for VDM. Okay, so any questions? No questions? All good? Okay, might take some time to digest, but so at this point, you should be able to do, or at least be able to address assignment 3. So replicate it. Okay, von der Marsburg showed you that after he trained it 100 times, he get these nice clusters. I haven't done it yet with the Python version, right? Which is good. You can sort of use what I have for the base and see if you can do it too. Okay? But that's the primary question for assignment 3 is to do it, to do von der Marsburg's, replicate his finding if you can. Okay? I do allow you, if you don't want to waste your time with the hexagonal nonsense, okay, you can try it with the standard square patterns. You can also do vertical, horizontal, you know, with a square. You can do that too, absolutely. All right? Just then modify the code accordingly. Okay? And again, how do you evaluate and visualize your performance? All right, so this is the primary goal for assignment 3, question 1. And the second one is optional, so really it's about number 1, okay? And the optional, I see you can modify, I put it there, if some of you have heard the MNIST stimuli. You know what that is? MNIST is, if you Google, this is MNIST, yeah, this one, okay? Let's click it, this one. So it's a collection of the same character, but written by, you know, handwriting in, you know, because 0 looks different depending on who writes it and when you write it and how you write it, you know. But they're all zeros. So, and then 1s and all that. So obviously this has something to do with the way our eyes recognize angles and stuff. It's all black and white. So can you figure out, like, if you have now a VDM, can you put it all together with, let's say, your back prop or whatever. However, you now have really all the pieces you need to create a super neural network that will be able to say, like, if you give it any one of these, it will be able to tell you it sees a 0, it sees a 1, a 2, or whatever. Okay? You literally have the pieces. If you think about it, you can. If you put it together, you can do it. All right? Just how? So that's the optional assignment 3. So this was one of those things like when we did our class in Illinois was we have undergrads to graduate students doing this course, and the graduate students have to do the optional part because you are graduate students, right? Okay, and all the more your PhD students. So the pressure is that, of course, as a graduate student, you can solve number 1 no problem, right? So that's why we give you something more challenging. Show us that you are beyond undergrad. You can do the optional level, so to speak. Yeah, I know there are undergrads here, so yeah. But it is optional. But I think it's a good challenge. It is something that will kind of test the final test of whether you've learned all the content in this course. Is if you can solve this problem using what we have, the various pieces we have. We know now you can do LLMs and whatever that will recognize this kind of thing. No problem. We know that neural networks can do it. That's not the question. The question is whether when we have these pieces, we can ourselves piece together a neural network with those principles to solve this problem in this way that we can explain, right? Because if I let the LLM or whatever machine do it, I can't really completely explain because a lot of the engine behind is hidden to me, right? I know roughly in principle what it's doing, but I cannot really confidently say every parameter, what was set, and how it worked. Here, because I built it up from scratch and with known principles that I know make sense neurally or don't make sense neurally, then when I get it to do it, then I can have a clearer way to explain. Or, in fact, say why I can't explain, right? Because it should make sense, but it doesn't, that kind of thing. Those are the more interesting things. Okay, so this is really the Olympiad level question. Out, right? It's if you combine this and then given these pieces, can you solve this problem like this? And no one really gave you the answer. You have to figure it out yourself. Okay, and we'll see. Okay, so it's optional, but the part 1 is the primary goal. So you can try, or at least you attempt to replicate von Neumann given the pieces that we have. Okay, so that will be it. That will be really the core part of this course. All the content that I want to transfer to you guys, the essentials, is up to this point has been transferred. Okay. The next few weeks, in fact, we only have 2 more weeks. We have next week, which we will evaluate the VDM in other ways, tools, which is, a flexible thing. Then the week after is a break. Is it 端午节? Yeah, week after is a break, 端午节, no class. Then the week after that, 6号是吗? Yeah, 30号. I originally scheduled something. Yeah, I scheduled this, but I will move it to the last week, 就6月6号. So that will be the last week. So this week, I will update it. There should be no class. This is 端午节. And so this June 6th will be the last class. So we have next week, and then a break, and then the last week. And in the last week, I encourage you guys. So in the last week, we are going to have a special guest monitoring from, is not involved. She's just here to monitor the class. Okay, she wants to see how people. 她是从那个应该是外文系吧 right? They have this project. It's a professor. She has a project, and she wants to take a sample of English learning courses. So she just wants to see how different classes deal with English being taught. And for example, Taiwan students do they have a problem with English? Taiwan teachers, do they have a problem with English, or you should use Chinese and whatever? So she just wants to sit in and observe. So the last class we will have just a silent visitor there, sort of, okay? And I think it's good because we will be just very relaxing, kind of talking about more general, broader issues to close up the course, okay? And these are issues to do with overfitting. This is the biggest problem, okay? And therefore, our solution to it, how do we do regularization, what does that mean, etc. And since I will be pushing this, this is a break, I will also then use that class to talk about recurrence and convolution and deep neural networks. Talk a little bit more. We talked about it somewhat, but we will talk about it more in the last class. And these are optional topics. They're not essentials, but they are real problems that engineering solutions face nowadays. And yeah, we can consider if those are problems for biological systems or not, okay? Not necessarily, okay? So that will be the last class, and so it's going to be relaxed, but I think you know, it should be fun as well. Okay, so that's it for today, really. I want to just like show you guys the VDM code in Python, and then next week we will evaluate it further. Hopefully I will have sorted out the little bug, okay? Any outstanding issues or questions about things? Assignments? Okay, if people need time for assignments, let me emphasize also, if people need time for assignments, I really have no problem. I can even extend the assignment all the way to the last day of class if you want. Okay, seriously, seriously. Okay, I know it's stressful, I know it's difficult. And so and for me personally, my goal here is not to make it difficult for you. My goal is to have you have the opportunity to try out, get your hands dirty, get your brain thinking about it and solving this problem. If you can fail, it's fine. The code can like break and you have, you know, but struggle through it and then compile your report to about your struggles, your success and your failure. This is really what I want to do in the class, okay? No way that you do short neural network and then like suddenly you're an expert in neural network. Of course not. That's not the point, okay? But this is your opportunity to deal with these concepts, deal with the implementation of it, deal with how to compile your experience, your method, your approach into something that is concrete and reportable. Because that's actually what's more important in the future as you take more projects. This cycle, okay, is what will get you to the eventual solution, all right? Not that you can solve it right now and you get everything now, but the process of it, okay? So because of that, I really, really don't care about like those kind of the dates and that. If you need more time, just let me know, okay? All right? If you have questions, let me know. Okay, so that's it for today. We end at 11:30, and next week we will have the final deal with the VDM model, and then that will be it. Okay. I believe people are busy with assignment 2, but I will be releasing assignment 3 today, later on after class. So you guys, if you guys have, some of you have already finished or are going to finish assignment 2, you can immediately move to assignment 3. Okay. All right, that's it. And so thank you very much. Some of you are staying for, there'll be Brain Hack School later this afternoon. I just want to share that Brain Hack School today will be a series of 2 industry speakers. One speaker is from Taiwan. For those of you who are not in Brain Hack School, it doesn't apply, but you are welcome to stay if you are interested because the speakers are not listed here. The speakers are one industry person, Sean Liu from Artist Bio. Sean Liu. It's a Taiwan company, Tsinghua. Yeah. Okay. He is in I guess biotech and stuff, right? Yeah. right. Okay, and he'll be giving sort of a industry academia synergy talk, and I think it'll be very helpful for those of you who are in brain hack school or in this field. If you are not, like I said, if you're not in brain hack school but you're interested, you're welcome to stay as well. It's hybrid, it will be online, but the link would be available. We will be doing sort of the live version link up to him from this room at 3 p.m. today. And then later on, at 4:30 p.m., we have someone from Carlton Chu from Google DeepMind. He will be giving the industry talk. Okay. He's a very interesting person, and it will be a very good, I think it will be a very fun session. Okay. He is, okay, yeah, so he is, a lot of people know him, or he knows a lot of people, or whatever, but then if you want to find out about what it's like to work in Google DeepMind, or ask him questions, advice on career, or whatever, he will be joining us from UK online, and again, we will be hosting the video session primarily here, but it will be an online link as well, all right? Okay, just to put a plug for this so that you guys know what's happening here this afternoon. And you don't have to be in brain hack school, but if you're interested, you are welcome to join. Okay, so that's it from me today, and I will see you next week. Okay, thanks.